We are in the control section, so let's look at an example of DC motor speed control, which is different from the converter that we just had. Okay, so DC motors basically convert DC electricity or electric power into mechanical rotation or mechanical movement. And the way they operate, I don't need to go and I don't want to go into principles and the operation of DC motor, that's another topic. But this is an equivalent circuit for a DC machine. DC machine has a field circuit and an armature circuit. So the field circuit generates a magnetic field, it's a winding basically. And then the armature again is a winding that is wound now around the rotor and it can spin. The field winding is on the stator, it cannot spin. And then when you apply voltage to the field winding, there will be a magnetic field there. And then now when we apply another voltage to the armature winding, you will see that the machine starts rotating. So it converts the electricity here, VA, IA, that will be the power or energy, and then into mechanical motion. So this EA is the internal voltage of the machine. We don't have access to that one. This is the armature voltage. These are the armature winding resistance and inductance. And this is the field circuit. The equations of this circuit, this is an electromechanical system. So it has a mechanical equation and it also has an electrical equation. And these two equations are connected together. So this is mechanical equation that shows the torque that the machine generates should balance the torque that is on the shaft of the machine, this tau prime, and the frictions, and also the inertia. So this is the inertia of the rotor, this is the friction, and this is the rotor torque. The mechanical equation is this one. This is the electrical equation on the armature circuit. This is simple equation here. So VA is RAIA plus LAD over DTIA plus EA. Now we need to know how much torque the machine can produce and how much is the internal voltage. Otherwise the model is not complete. We don't want to prove, but you can prove that the armature voltage is proportional to the magnetic field, the magnetic flux phi, and the speed of rotation. Multiplication of these two. And especially if the flux is constant, you can say the armature voltage is proportional to speed. That's it, this equation here. And the torque is proportional to flux into the armature current. And again, if the flux is constant, you can say it's proportional to armature current. Now, if you substitute these two into these two equations, you have a complete model of the system. Two differential equations. And now once you have differential equations, you can take Laplace transforms from differential equations and derive the transfer functions. Put everything together, just to go a little faster, you will see this will represent the system. We have armature voltage minus the induced or internal voltage. This is EA. And then this is the voltage across the armature inductance, armature winding, divided by its impedance becomes the current. Current multiplied into the constant, machine's constant, gives you the torque. Torque minus the load torque divided by Js plus B, this is this equation here, gives you the speed. And we use capital letters in the Laplace domain. It's all right if you use lowercase, but normally we use capital letters. So this diagram basically shows transfer function model of the DC machine speed control. Yeah, okay. If you want to control the speed using the armature voltage, you see, this is the input. Armature voltage is the input. The speed is the output. This is disturbance. Because we normally, in applications, practical applications, we do not have control over how much load is on the shaft of the machine. and it can suddenly change at any time, right? So that we consider that as a disturbance. There are uncertainties. Any parameter you see here can have uncertainty. K, LA, RA, K tau, J, B, these can have all uncertainty. Are there some unmodeled uncertainties? Yes, because we made some assumptions in deriving these equations. So this model has uncertainty, parametric uncertainty, and also has unmodeled uncertainties. Okay, a little bit playing with this system. We need that also later for converters because it's similar. If you combine the transfer functions, you know omega m is this transfer function into this input, and this input is this minus this one, and this is equal to this one, into k tau. Just combine these equations, play with the equations. You can derive one single equation for omega m versus the input and disturbance. Now this equation, now you can put it together in this form. VA into G1, that's this one, plus disturbance, and that disturbance is negative of the load torque, multiply into G2, that gives you the speed. So you remember I said, we've told you before, there are three ways of modeling the disturbance, either at the input or the output or somewhere in the middle. This is basically somewhere in the middle for this system. Okay. For converters, sometimes this disturbance is at the input, sometimes output, sometimes in the middle, depending on the type of converter that we use. Okay, now what is the control problem here? Statement, we want the speed of this machine, of this motor, to be at a given number or to follow a given pattern, if you want, despite the disturbance and despite the uncertainties, modeled uncertainties or unmodeled uncertainties. How do we do that? There are two ways of doing, one with feedback, one without feedback. Already we said for power electronics we need feedback, but not always. Sometimes with non-power electronic systems we can do without feedback. What does it mean without feedback? Without feedback means you want this speed to be this amount, and then you know the mathematical model of the system with relatively good accuracy, may not be 100% accurate. You know, based on some calculations, that if I apply this amount of voltage here, I will get that speed. So you apply that voltage. That's it. So that's called open loop control, without using any sensor or without using any feedback. So if you want to show it in diagram, it's like this. I have this physical system that I want to control, and I don't know how much is this input, but I know how much is the desired output. So I process the desired output based on the equations of the system and find out how much input I need, and I apply that input. You remember we calculated M, for instance, for the converter, it became 0.425, and we applied 0.425. That is open loop. But we realized it's too sensitive. Then we close the feedback. If we did not close the feedback, that becomes an open loop control. Advantages, very simple. No sensor, very economic. No sensors, and no stability concerns. Because if physical systems, normally they are stable by themselves. So if you don't close a feedback on them, they still remain stable. Disadvantages, as we said before, sensitivity to presence of disturbances and also uncertainties. Another disadvantage is that you cannot, like I said, if it's stable, it will remain stable, but at the same time, you can look at it as a disadvantage in the sense that you cannot change it a lot. If it's stable, but it's not really very well in terms of oscillations and dynamics, you cannot improve it. In open loop, you cannot significantly change the dynamic of the original system. You can only make some adjustments. You cannot change dynamics. So generally speaking, the open loop control is only suitable for the systems where the levels of disturbance and uncertainty are sufficiently small and the system is initially well behaved. A power electronic converter is not like that. Right? But if you have a DC machine with a lot of, passive elements in it, and you may say, okay, and you want to run that DC machine in an environment which is very clean environment, not much changes, and like for instance, I know that satellites they use open loop control because they are not facing any friction or disturbances. So if you design the machine very well, so they pay a lot to design the machine very accurately. So all these parameters J, B, R, A are accurately known. And then you just put an open loop control. It works. Then you want this satellite to go around with a given speed. So you apply 100 volts and will keep going at the same speed. Nothing is going to change it. So for instance, here, that's what we said. We have this machine. Then we want to apply this. So when we say, again, in simulation, you just put it that. But in practice, what does it mean to put it that? It means you need to generate that voltage. How do you generate that voltage? That voltage you need to generate using, often, depending on the size of the machine, using a power electronic converter, which in this context is called power drive or motor drive. So in this context, this controller is called motor drive, right? But it's a converter. It's a buck converter, boost converter, or bidirectional VSC or something like that. Okay, so the simplest controller that you can use here is a constant K. And then you only need to adjust this K such that the amount of voltage that arrives here or here is sufficient to run this machine at that given speed. So you can solve the equations and derive it. So K into G1 0 into G2 0, that's the DC gain of this system. That will be equal to K tau divided by this one. You put S equals 0. That should be 1. And then from there you find K. Okay. Now, closed loop or feedback, we already talked about that, is that you measure the output, or at least the output. It could be more than output. You can measure more than output, other things also. So at least you measure one variable, normally the output, and then you compare this variable with the desired value. You generate an error, which we call it tracking error. This is tracking error. And then depending on whether this tracking error is positive or negative or 0, you calculate how much voltage you need to apply here. If the tracking error is positive, for instance, it means that this is smaller than this one, so the speed is low. You need to generate more voltage, so you increase the voltage, right, and so on. Advantages: can in principle respond to disturbances, can in principle respond to uncertainties, right? And can modify the original dynamics. I will show that in a moment, what I mean by this. Disadvantages are you need to add sensors. Sensors add costs, but often costs may not be the main concern. The other concern in some systems is that sensors can have failures and errors also. So in other words, you add one component to the system that adds one point of failure to your system. And sensors come with noise also. Okay. And the design stage can become a challenge. Now, if you have a feedback, and if you don't design this properly, you can even destabilize the system. And rather than fixing the system, making it worse. Why? The reason is here. Let's say this is the transfer function of the plant. This is the transfer function of the controller, right? So output is G into C into the error, and error is YD minus Y. So from this equation, you can derive the transfer function from the desired desired output to the actual output. That will be this transfer function. So in open loop, the transfer function is just g into c. In the closed loop is g into c divided by 1 plus g into c. A very complicated, you can say, expression. And in terms of these polynomials, if you put that in the equation, you will get this one. So you see the denominator of this expression is not equal to the denominator of the plant, is not equal to even to the denominator of plant into the controller. It's a mixture of denominators and numerators. So let's say you do not design numerator or denominator of the controller properly, and some of these poles go to the right side. It becomes unstable. So that's why stability becomes really important in feedback control. And that's the first and foremost property that you want to achieve, stable. And then once you achieve the stability, the next is performance. Now you need to achieve good performance. Okay. So this is the block diagram of this feedback control system. This is the plant, controller, and the sensor. We add sensors. Sensors basically adds a noise. This is the way we model the sensor noise, and it may have a transfer function depending on how fast your sensor is. Now, if you calculate the sensitivity of this system or closed loop transfer function to the open loop transfer function. So very simplified. Look at the open loop transfer function as a parameter and look at the closed loop transfer function as the function. What is the sensitivity of that one? You will realize it's equal to 1 over 1 plus L according to the equation that we derived. So this is called sensitivity function of this feedback system. So you immediately see that if L of S is large, this system is less sensitive, okay, to the parameters. Now, if you look at the transfer function, this system has multiple transfer functions that I derived. The most important one is this one, the output to the set point or to the desired, and the error to the desired signal, and the output to the disturbance, right? And the noise transfer function, output to the noise, multiple transfer function. For these three, 1 plus L appears in the denominator, and then for these two, basically, and nothing in the numerator, right? So we want this transfer function to be close to 0. So by increasing L, we can bring it 0, because that means you can remove the disturbance. If you want to make it less sensitive, again, you need to increase L. And if you increase L, this transfer function goes to unity. So that's also good, because the output becomes close to the set point. However, this transfer function also becomes large. In other words, the system becomes more sensitive to noise, to the sensor noise. Or, generally speaking, sensor errors. If there is any error coming from the sensor side of the system, and then you make this system very fast or make the open loop transfer function very large, which is basically the same thing, then this system becomes sensitive to noise. So what happens is, in practice, we need to follow this guideline. Disturbances and the commands or desired signals happen at low frequency, and noise typically happens at high frequency. So if we choose, if we shape L of S, which we call it, by the way, loop gain or loop transfer function, if we shape that transfer function to be large at small frequencies and to be small and at large frequencies, then we can make sure that it has a good noise property and it also has a good tracking property. Okay? So the conclusion is from this discussion is that in any control system, the loop gain or the loop transfer function of this system must be shaped or designed such that at low frequencies it's large, at high frequencies it's small. This will guarantee that the control system is not very sensitive to disturbances, it's not very sensitive to uncertainties, and it's not very sensitive to sensor noise. This is the general guideline that we need to follow. Okay, so body command in MATLAB shows this diagram, and then you can use that to shape the plot. Stability margins. There are two stability margins that are very important in this control system. One of them is called phase margin, and one of them is called gain margin. And delay margin is also related to the phase margin. They are defined this way. If I have this control system and I design this successfully and it has a good performance in the simulation, okay, now I know in practice there will be some delays in the system. That delay is e to the negative ts, and that actually does not change the magnitude of the loop, because e to the negative ts when s is j omega has unity magnitude, but it will change the phase angle of the loop. How much phase angle I can tolerate before this loop becomes unstable. That is called phase margin. For gain margin, we say, if this whole thing here, I don't know this whole thing exactly, and it can go up or down, especially the higher upper side. How much I can increase this before the loop becomes unstable. That is called gain margin. So people have realized throughout the years that these two margins, phase margin and gain margin, are very convenient, very important, and very informative to tell you a good indication of how robust your control system is. One of them talks about delays in the loop, one of them talks about gains or change in the gains of the system. Okay. And then once you have the phase margin, you can find delay margin. Delay margin into that frequency that the phase angle, the delay margin happens, phase margin happens. This command in the MATLAB calculates phase margin and gain margin, so you don't need to calculate it yourself. Okay, now let's go back to the speed control system, DC machine with feedback. Okay, so this is the transfer function of the system. We put one controller here and we close the feedback. I'm going to design this one. Okay, my objective is to make sure that the output, the speed here, will follow this one, even if some parameters are not exactly what they should be or what I assume them to be, or even if the load disturbance or load torque changes as a disturbance. Where should I start? The starting point would be the simplest one. Let's say CS equals K. And I told you this is virtual resistance. CS equals K. It's called proportional control. Right? Whether you put K here or you put it here, it doesn't matter. It's the same thing. Okay. So let's start with this K. I put Kp for proportional. Then your loop transfer function becomes simply the transfer function of the plant into this Kp. So in terms of body plot, the magnitude of L, when you multiply into K, magnitude goes up when K is larger than 1, or goes down when K is smaller than 1. Right? Phase angle does not change. Phase angle does not change. There is another tool that we use here. Some of you may be familiar, but I don't think I have time to explain that. It's root locus. This diagram, root locus, basically shows how the closed loop poles change when you increase Kp. So you start increasing Kp from 0 all the way. Originally, the poles are at -1 and -2, and they approach each other, and then one of them goes up, one of them goes down. This is called the root locus, and this is called the body plots. So combination of these two tools, root locus and body plots, gives you a sufficient background to design the controller. Let's say I want to have this amount of phase margin and this amount of gain margin, right? Phase margin and gain margin, you can read it from this plot or you can use the MATLAB command margin. So change K and see when you get the sufficient gain margin and phase. You may not be able to get sufficient for both of them, but you at least one of them you can guarantee. And if you cannot get both of them sufficiently, that means this controller, this simple controller, is not sufficient. You need to go one level higher. Okay. So here's the explanations. The second type of controller, one level higher, is proportional derivative, which is called PD. Now we have one proportional and one differentiation. And what it does, it basically, if the original poles are here in the root locus, it actually pushes them to the left. When you push the poles more and more to the left, you can make the time constants of the system smaller. The response becomes faster. So with this one, really you can make the system significantly faster if you want. But at the same time, if you watch the phase margin and gain margin, you will see that you immediately start losing phase margin and start losing delay margin as well. Very reasonable. And that's why I said in the converter, if you make it faster and faster, your delay margin goes down. So it's a trade-off between how fast I want my responses to be and how much delay margin I can sacrifice. The next one is proportional integrating, or PI, which has a proportional term and an integrating term. This is a very common controller in industry, in converters as well. So what it does basically, this integrator here, which supplies one S in the denominator, which means infinite gain at S equal 0. So at S equals 0, when you approach S equals 0, this gain keeps going up and up and up and up, right? And theoretically, at S equals 0 is infinity. So that means when this gain is infinity, 1 plus L in the denominator, the error becomes 0. So there will be no tracking error in the steady state. So that's what an integrator does. Integrator removes the steady state error. But if you look at the poles of the system, you see that it does not push the poles to the left. So generally speaking, it cannot increase the speed of the system, but it can remove the steady state errors. So if you really look at these controllers, one of them works on the transient response without changing the steady state. One of them works on the steady state without changing the transient. Now you can combine them and then derive a PID controller. So PID. And this PID controller gives you 3 degrees of freedom: proportional, integrating, and derivative. If you design these 3 properly, you can maximize the benefit from this feedback loop in terms of speed response, speed of the response, in terms of the phase margin, delay margin, and those kind of things, and steady state error. Okay, so these things try to read through, and I think you should not have difficulty understanding them. And there is a MATLAB file that will be shared with you. That MATLAB file generates all these figures, so you can see how these figures are generated in MATLAB. So here is the conclusion. The response of the open loop system, the response of the proportional, the response of the proportional derivative, the response of the proportional integrating, and then finally the response of PID. So you see proportional speed up the response like a virtual resistance, but it cannot remove the steady state error. There will still remain some steady state error right here for for the proportional one. If you want to reduce that steady state error, you need to increase k and make it faster. But by increasing k, your phase margin will go down. So you don't want to do that. You need to make a trade-off between phase margin and steady state error for PD. For PI, that's this one, the steady state error is 0. You see, eventually, it may take some time, but eventually we'll go to the speed that you want. But it's not very fast. If you want to really make it faster, if you need to. If you don't need, that's okay, you can stop here. But if you need to make it faster, you cannot work on PI much because it generates large oscillations if you try to make it faster. Now you go to PID because you say, I'm good with this one. Steady state error is 0. Oscillations are good. I just want to make it a little faster. So you add one derivative because derivative makes it faster. And that's what you get here. Okay? All right. So PID, this is the way we implement PID for this machine, again for DC motor for instance. This is the actuator or the drive that generates the voltage. Now this is the proportional term. For the derivative, we have to put a filter on the derivative. This is a practical consideration because if you don't put a filter on the derivative block, it will amplify the noise. You can just imagine in your mind, if you differentiate a noise, what happens? Right? It becomes large signal. So you need to filter the noise first a little bit and then differentiate it. For the integrator, another problem happens that we call it, it's called wind-up problem. Wind-up problem happens because in all practical systems we have limitations. If it's a drive, a motor drive, it has a limitation. It can only generate this amount of voltage, right? Even PWM has limitation, right? Any physical system has limitation. So if you push the system or push the response of the system or the operation of the system to the limits, it will actually cut the signals at that point. It cannot generate more than 400 volt. Stays there. If you ask it to, if the controller asks the drive to generate 500 volt, and its limit is 400, it cannot generate more than 400. It stays there. So it's just like a model like this. It saturates. So when saturates the output, during this mode, during this extreme mode, that sometimes happens in physical systems, and we will see in converters also it happens a lot. During this mode, the integrator starts growing the output without really having any impact on the system, because it's in saturation. But the integrator keeps integrating, integrates, and the output of the integrator winds up, goes up, 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 up. Now, when the system eventually, assuming that the system is stable, comes back to the linear mode, it takes long time for the integrator to wind down. So the system will start oscillating with large and long oscillations. In order to prevent that from happening, you have to put a mechanism called anti-wind-up. You have to prevent the integrator from winding up. There are multiple ways, but two common ways of implementing is that you can take the input and output of this limiter block, let's say 400 volt, and now your command goes to 500. So the difference between them is 100. So that difference, you bring that difference, you multiply into a constant, and you subtract that from the input of the integrator. So this way you say, if the system goes to the nonlinear mode, pull down the input of the integrator, prevent the integrator from winding up. So by properly designing this K, you can prevent the integrator from winding up. Another approach, which is nowadays very much used, is also very simple to implement in digital control, is just to freeze the integrator. Whenever you enter into nonlinear mode, stop the integrator. We call it freeze it. Stop updating the output of the integrator during that time, and then when it comes back to the linear mode, again continue. So each one of them has a different different properties and different responses, but you need to simulate. MATLAB nowadays, the blocks in MATLAB has both options, so you can choose and see which one gives you better responses. Another thing I can say here, it's not very important, but it's say this Kp, which is going from the error to this one, you can break it down into two portions, alpha Kp and 1 minus alpha Kp coming from output. And alpha is a number between 0 to 1. So in other words, you put one component of this one in the feedback. This is like a virtual resistor, exactly. If alpha is equal to 0, this is removed and this becomes exactly like a virtual resistor. Remember? Now you can prove, and I think I have proved here, this arrangement will not change the stability properties of this system. In other words, you have the option to do that. So why would you do that? I will tell you tomorrow in the class that if you play with this alpha, you can fine-tune some of the responses, but not significantly. Okay? All right. Some feedback loop properties. Already talked about steady state error. I told you if you have an integrator, then that it supplies infinite gain at s equals 0, so it removes the steady state error. This is a known concept in feedback control that at any frequency, if your loop or controller supplies infinite gain or very large gain, errors at that particular frequency will be removed. So if you have 1 over s, which is integrator, it supplies infinite gain at s equals 0. So it removes all the errors at frequency 0. What is frequency 0? DC. So if your command is DC, and then you have an integrator, it will eventually get there. It may take a long time, but it will eventually get there. Steady state error will be removed. Now, in converters, sometimes we need to remove the error at 60 Hertz or 50 Hertz. I'll talk about that later when we get into single phase inverters, basically. This one, forget about it, it's not important. Pole location and transient response. I alluded to that, but without explaining much. And it's very clear that modes, every mode is e to the p into t, and p is the pole. So if the pole is further to the left, that means this mode is faster. So every single mode typically has a shape like that. Exponentially goes up, let's say, when you apply a step to the input, to their set point. And it takes tau seconds to reach 63%, and that's tau seconds, it's equal to 1 over p. You can prove it mathematically, very easy. So after 1 over p seconds, let's say your pole is negative 1000. 1 over 1000 is 1 millisecond. So after 1 millisecond, the response of this converter is at 63%. After 4 time constant is at 98%. After 5 time constant is at 99%. We call it settling time. I already used that in the example. Okay, very simple concept. So that's for first order system, or when the pole is real. But sometimes happens that we have 2 complex poles. For 2 complex poles, this discussion is not valid. For 2 complex poles, if you have a system with 2 complex poles, the response becomes like this. And in other words, it has an oscillation and it has a rise time or settling time and these things. And these you can imagine these things are in trade-off. If you try to make it faster, or reducing the time constant or reducing the settling time, your oscillations may grow larger. So we can find an equation for this peak value. We can find an equation for this peak time for a second order system. These are the equations that I have derived somewhere. Yeah, here. This is for the peak time. This is for the peak value. We call it also overshoot of the response. And then these are basically depend on two parameters are zeta and omega n. Zeta and omega n are defined as if the poles are here and here. So the magnitude of the pole to the origin is called omega n. And the angle that makes with the real axis on the left side, if you call it theta, cosine of that theta is zeta. Right? So if you define these things properly, in other words, in the polar coordinates, then you can derive these two equations. Okay. For those of you who haven't taken control course, you can look at any basic control course and you will see the derivation of these equations. Okay, now one important question about second order systems for you as researchers is that if I have this response, let me see if I can draw another response. If I have another response like this, which one of these two is faster? Red one is faster. In what sense? Reaches the peak faster, but it doesn't reach the steady state faster. Yeah. So that's the thing. For the first order system, there is no ambiguity. But for second order system, there is an ambiguity. We cannot just simply say this is faster than the other one. You need to explain in what sense. If you mean in terms of rising to the final, yes, the red one is faster. If you mean in terms of settling to the final, no, the blue one is faster. So these terms should be used carefully as researchers, right? Don't use them very, very loosely. Use them very, adequately use them. I think I will stop here. I'm a little bit behind my schedule, but that will be the feedback control or the state space design. Probably 1 hour for that. We'll do that in the morning. I don't know. Chandra Shekaran, do you want me to continue a few more minutes or you can stop here? Yeah, that's a good idea. So let's spend a few minutes with questions and then I will start the other chapter tomorrow. Yes. Yes, delay. Yes, if you know maximum phase margin, and phase margin happens at a given frequency, that command margin in MATLAB gives you 4 parameters: gain margin, phase margin, frequency that gain margin happens, and frequency that phase margin happens. Right, exactly. So if you divide the phase margin to the frequency that phase margin happens, that becomes delay margin. I don't think the MATLAB command directly gives you delay margin. You have to calculate it yourself. Any other questions? Okay, feel free to email me, even though maybe I may not be able to answer emails during this time that I'm here, but later on, if you have any questions, feel free to email me. Introduce yourself so I know you're coming from this class. And if you have any questions, I can answer your questions. Yeah. All right, so like I said, I'm a little behind, but it should not be a big problem. We try to cover. I already gave a little warning to Dr. Chandra Shekaran that we may not be able to complete 100% whatever we promised, but it will be close, maybe 80% to 90%. We'll try. I'll try my best. Now I'm looking, it should be a course more than 5 days. If we really want to go slowly. This course, I teach it in 1 full semester. And again, I skip some material. So it's almost twice in terms of hours than this class, right? Because this class is how many hours? 14, 15 hours. So 1 semester is 36 hours. So it probably could have been a 10-day course. But I'll do my best. Okay. Thank you, everyone.